Okay.
Do you see my screen now?
Yeah.
Yeah, should be good. Okay. All right.
Okay. Are you ready?
Yeah.
Okay. Good afternoon. Welcome everybody to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Professor Hamid Usefi, who is also a co-author friend of mine. After obtaining his PhD at the University of London, Ontario, under the supervision of David Raleigh, Hamid first moved at the University of Vancouver for a postdoc position, and then to the Newfoundland, to the Memorial University of Newfoundland in St. John's. His research activity mainly focuses on Lie and associative algebras and on some aspects of computer science. In the talk of today, Hamid will speak about polynomial identities, group rings, and developing algebras. Please, Hamid.
Sure. Thank you, Salvatore, and thank you, Ivan, for the invitation. These are one of the benefits of having the COVID, to be able to host this sort of seminars virtually. So it's a great thing you guys are doing it. Yeah, today I want to talk about polynomial identities, group rings, and enveloping algebras. I'm going to go way back and essentially see where try to explain a little bit where the polynomial identities started initiating and motivation sources, and so where that led us and where the theory, essentially how it was developed by a couple of influential people, and then at the end to report some of the work that the past couple of years myself and my collaborator, especially Salvatore, we tried to do. So I'm going to start with the Burnside problem. You can state this problem in the first group theory for undergraduate students, saying that if you have a group which is torsion and finitely generated, is it finite? So this was the general Burnside problem from 1902. So you quickly realize that you have to put some restriction, otherwise you can get a counterexample right away. So then you put a finite exponent, saying that every element has a finite exponent. Can you bounded Burnside problem says that is every finitely generated group with finite exponent finite. So we can formulate this in a better way by forming this group. We call it B for Burnside, which is generated by R elements, and you divide out by, so you take the free group and you mod out each generated by the exponent of E. So this will be sort of relatively free group generated by R elements, and every element have exponent E. So then you could ask whether this group is finite. So this is the biggest group you could have in R generator and of exponent E, and every other group will be a quotient of this B, R, and E. So the question is whether B, R, and E is finite or not. So that is the modification that we do to the Burnside problem. So Burnside himself investigated this group. It makes sense to investigate for smaller numbers. It could be very combinatorial, the sort of problems you're working with this free object with the small exponent. So that's, but you could do so much when this exponents are small, and after a while, after exponent 3 or 4, it gets out of hand. You can't really extend it further. So Burnside himself tried B, R, and 3, where the exponent is 3 or 4, and showed that those are finite. And then at the same time, you could look at the other groups. And for example, matrices, he showed that the same holds. And every finitely generated torsion subgroup of GLN also has finite exponent. So these are the people like Burnside, Shor, these are the pioneers back then. And then the famous counterexample to this problem, general universal problem, was given by Golod-Shafarevich. So the example is very interesting because even though we are looking at group now, the example starts from algebras and has a very combinatorial flavor. So I'll explain some of the bits of the example, how that is developed. And the similar question that we are looking at, the Burnside problem, it can be also stated for Lie algebras, or for rings, or associative algebras. You just have to adopt the terminology of saying the torsion. You adopt the torsion to nilpotent, for example, when you're talking about associative algebras, or to adjoint nilpotent, you're talking about the algebras. So this Golod-Shafarevich counterexample was essential, sort of form a very good foundation of what is true and what is not true, and then where else to look for positive or negative answer. And after that, Aiden and Novikov showed that B2 and E is infinite. So if you get a 2 generator, and as long as E is more than a certain number, and that number is very interesting how they come up with that number from the construction, but nevertheless, this sort of groups is infinite. So that's again a counterexample that come from a different angle from Aiden and Novikov. Now, I want to show a little bit about in a bit about the Shafarevich construction. So let's take the intersection of all normal subgroups of finite index in B. So then this, we call this R, and then any finite degenerator subgroup of exponent n is an image of R. So essentially, we are in this variety, we are taking the largest object that exists, and we ask for that object whether that object satisfy that criteria that we're looking for the Burnside problem. So in other words, if R, which is generated by D elements and of exponent n, so this is the largest element in that variety, if this R is finite, then any D group of exponent n is also finite. So we can bring our attention to this relatively free object in that variety. So we shall see that, okay, so Burnside problem had a counterexample. B has a counterexample by Aiden, also by Shafarevich, but R will have a positive solution. So let's look at those, and that's essentially what first chunk of the talk is about. So Shafarevich example, counterexample, it is like it's very algebraic and combinatorial. So you start with the free associative algebra, and you take an ideal of T generated by a set S of homogeneous element. Then T mod I will be infinite dimensional, provided that a certain condition is satisfied by the number of homogeneous elements inside S. So here I is an ideal of T which is generated by S, and S itself consists of homogeneous elements of T. So we're only asking the number of homogeneous elements of each degree. We are asking it to be bounded by D minus 1 squared divided by 4. In particular, if you take D equal to 3, so 3 generator, then we are asking that R will be at most 1 for each of the, so you'd have at most 1 element in I of each degree. So that is the second part of the construction. So you take free associative algebra in 3 generator over a countable field. So then T itself will be countable. So you can order or count the elements of T. So you'll have the monomials, and then you have the linear combinations using the elements of the field. You can count them up and sort them out. So you can enumerate those elements as T1 blah blah, T1, T2, and so on. So now we're going to come up with an ideal, as with regards to the first part, an ideal I and a subset S. So the ideal I that we construct is using this terminology. So you pick every of those elements of T that we enumerate them, we take them to exponent of M1, and then you jump to the next level so that there is no overlap. So you will see that this ideal I will have at most one element of each degree, and so T mod I is nil, but it is infinite dimensional by the first part. Okay, so keep this T mod I in mind. So for now, it is just algebra, but we're going to go to groups now. How is that related to group theory and the counterexample to the Burnside general Bessel problem? Well, you take a field of P elements, P being a prime, and then take these generators. So if you go back to the slide, so you have T mod I, which is an infinite dimensional algebra. You take the generators of this algebra, you denote them by AJ, so xj plus I are your elements. So we consider the multiplicative semigroup G generated by these three elements within T mod I. Now we're going to observe a few things. First of all, each of these elements, A1, A2, A3, well, 1 plus A, you're looking at the group, multiplicative group generated by A1, A2, A3. So 1 plus A to the power of Pn, characteristic is P, is 1 plus A to the power of Pn. But A is xj plus I, so and each of the xj's are nilpotent modulo I. So A to the Pn is 0 modulo I. So in other words, 1 plus A to the power of Pn is 1. So 1 plus A has an inverse, and in particular, G is a group, and 1 plus A, being an element of the group, has a finite order because of the power of Pn is 1. So G satisfies the conditions of GBP, and yet we have to yet show that G is infinite, and this part of it is not very hard to see, because if G were finite, then you take all possible linear combination of elements of G, and it will form a finite dimensional algebra B. But then you take these elements 1, A1, A2, A3, generate T mod I, so we get that B, which is T mod I, is finite dimensional. So that is a contradiction. So yeah, this was the example of Golod-Shafarevich. I tried to give an overview of the construction. So what else is there after this? So we have this counterexample, but then remember we had that group R that we constructed. The other developments in this area was, of course, the great achievement by Thomson, who got the Fields Medal by showing that all finite simple groups of odd order are solvable. And this paved the way to classify finite simple groups. Now, to come up with the restricted Burnside problem, there was a lot of work related to Lie algebras and Lie rings, and try to bring the problem over to the other categories as well. So you can associate a Lie ring to every group by considering the lower central series of G, and then you take the direct sum of these quotients of Gi mod Gi plus 1. So Gi is the ith lower central series of G, so commutator. So you take these consecutive commutators, and then you take these quotients. When you direct sum them, you can define a commutator and addition on these direct sums, and this makes this L, which is constructed from G, to be a Lie ring. And if you go over the field of P elements, it will actually be a Lie algebra. So if G has an exponent P, then it is it's not too hard to verify that LG, the Lie algebra constructed using this construction associated to G, is P minus 1 angle. So P minus 1 angle means that add of each element is nilpotent of index P minus 1. So in this case. And there was a lot of work by Lazard and Hickman. Hickman gave a talk in the ICM of 58 about Lie ring methods in group theory and these sort of constructions, how you can use them in group theory. So these are all paving the way to come up with a solution to the restricted Burnside problem, because, for example, Khosrokhin showed that every Lie algebra over a field of P elements whose P-1 angle is also, he showed that is locally nilpotent. So remember that we call an algebra nilpotent or nilpotent if the bracket of every n elements of it is 0. Now, coming back to the restricted Burnside problem, remember that we took the quotient of B over K, so we called it R. Then L of R is the Lie ring associated to this R is nilpotent. In other words, so you take the lower central series of R, Ri is equal to for some index I, Ri and Ri plus 1 will be the same. Now, there's a little bit of, so I'm provided here a little bit of steps of how you get there, which I'm going to skip. But what is important is that not only that, but the potent class of R and L of R will be the same using this construction. Now, this brings up us to the work of Zelmanov, which gave him the Fields Medal. Well, so let's say, first of all, he generalized this first result of Khosrokhin by saying that, let's recall the definition of n-angle first. A Lie algebra is said to be n-angle if, so each add of x is nilpotent. Or in other words, if you take the bracket of y and n copies of x, you get 0. So Zelmanov in 1991 showed that every Lie algebra whose n-angle, so we have this sort of bound on the angle of each element, angleness of each element, over a field of characters 0 is nilpotent. So this is a very strong result. We don't have any restriction on the finitely generatedness of the Lie algebra. So the only restriction we have is that the Lie algebra is n-angle. So in other words, every element x is at nilpotent of index at most n. Well, this result, although it is true and is very strong in characteristic 0, is not true in other characteristics. So there are counterexamples of non-nilpotent and infinitely generated Lie algebras that are P-2 angle. Then Zelmanov extended this result to Lie rings. So in 1991, he again showed in a separate paper that every finitely generated Lie ring satisfying an angle condition is nilpotent. Then he ties back using similar constructions that we mentioned, using so you can associate a Lie ring to every group. He came up with a solution to the restricted Burnside problem for groups of odd prime order. And in a subsequent paper, he wanted to tackle the case of groups of even order or exponent. And then in this case, he had to use Jordan algebras. So I'm not going to go through the details of the constructions. There's heavily detailed involved, but this is the general scope of the work that was done. Like I mentioned, you could do the similar question in different varieties of different categories. For example, if you come to associative algebras or Lie algebras, so let's say for a second, Lie algebras, in associative algebras, Courage asked, are algebraic algebras locally finite? So algebraic means that every element of the algebra satisfies that, so there is a polynomial so that f of a is equal to 0. So in other words, the exponents of a, little a in a, are linearly dependent. So that's the definition of algebraic. Now, this sort of relates to the Burnside problem, because there we were asking for a finite, every element having finite exponent, whether we can prove that the group is nilpotent. But so having algebraic, we will see that it is not enough. So you want to specify a certain relation. In other words, we're going to focus on nil, saying that so x being nil is a special case of being algebraic. And so we can formulate this question. Courage asked, is every nil algebra locally nilpotent? Okay. So in other words, if you take any finitely generated subalgebra of a nil algebra, can you prove that it is nilpotent? Then obviously the Golod-Shafarevich example that we just saw shows that it is not. So we saw that the quotient of T mod I, which is nil, but it is infinite dimensional. So what else can we do, or what can we say, or what sort of restrictions do we have to put so to get some positive answers? And this is where this theory of polynomial identities started to develop. First of all, Kaplansky and Levitsky showed that a nil ring of bounded index, so in other words, if there is an n so that every x to the power of n is 0, they showed that is locally nilpotent. So in other words, if you put this here, so you're not putting any bound on the nilpotence of the elements of the nil algebra. But if you put a bound, then you get a positive response, and that is the Kaplansky and Levitsky. And then within that same area, other people like Hall were developing, were looking at different things, and they came up with this identity that the division ring, a division ring. So he was interested in some algebraic geometry and other topics, but he suddenly came up with this sort of problem, and he realized that if you have a division ring that satisfies this sort of, now we see it as an identity, but back then it wasn't clear. He couldn't structure it well. He said that if a division ring satisfies this sort of identity, then the division ring is either a field or the quaternion algebra over its center. So these are the first glimpse of the theory of polynomial identities. And similarly, for example, Jacobson showed that if you have a ring that satisfies xn minus x equal to 0 for all the elements of the ring, then that ring will be commutative. So in 1948, Kaplansky wrote a very influential paper, essentially summarizing and giving the structure of the theory so far. And so that paper was fundamental because it gave the structure and a way to see how things are evolving. Now, what is a polynomial identity? You take the free associative algebra, let's say in finitely managed generators, or if you want in countable generators, depending on the application or where you want to apply it. Then an element of this free associative algebra is called polynomial identity of a ring R. If when you substitute into variables of f, elements of R, you get 0 for any such substitution. So then f will be called a polynomial identity of R. Now, we say that an associative algebra satisfies a polynomial identity. You can form it by saying that any homomorphism from the pre-associative algebra to the algebra A takes your polynomial f to 0. So those are the substitutions that you make. They go to 0. So then we can now see that an algebraic algebra of bounded degree satisfies a polynomial identity, and an important contribution to the domain was made by Brel, saying that any affine PI algebra over a field has finite Gelfand Krylov dimension. And for the proof of this, he used this Kirchhoff height theorem to be able to show the growth of such algebras or polynomial. So you could see how this theory developed, because, for example, if you take a matrix algebra over a commutative ring, M2 of C, we know that every matrix satisfies its own characteristic polynomial. So being of this form, lambda squared minus trace of m lambda plus determinant of m squared equal to 0. So because trace of a bracket of two matrices is 0, then we can see that so bracket of m and n, or in other words, mn minus nm squared, is a scalar multiple of the identity. So in other words, if you take mn minus nm and substitute it in lambda here, so this part will be the trace of the bracket, which will be 0. So you get mn minus nm squared being a scalar multiple of the identity matrix. So in other words, the bracket of m and n squared will commute with every element or every matrix of M2MC. So this way we have constructed an identity of degree 5 for M2 of C. So in other words, this is an idea, we call this a central identity for 2 by 2 matrices. And you could ask whether similar phenomenon does happen to higher matrices or not. So Levy generalizes this S2, we call standard identity, to higher degrees. So there are a few facts that SK is multilinear and SQ symmetric, and Mn of F, n by n matrices over a field satisfy standard identity of size n squared plus 1. This is actually true for any algebras of dimension n. And then Levy showed that Mn satisfies Sn squared minus 1. But that was enough. You want a tighter bound. And so first of all, Mn does not satisfy 2n for any k is smaller than 2n, including 2n itself. Okay, so the 2n was the sharp bound that was speculating people. And then finally, Amitzer and Levitsky showed that Mn satisfies 2n. So 2n was the sharp bound that they were trying to see what happens one way or the other, which leads so this was also the results of Amitzer and Levitsky is a fundamental theorem in the area. And finally, so we have this fundamental theorem that if A is a left primitive algebra and M a faithful simple A module, we take the endomorphism of M over A, then we can give a structure to A in terms of the D. So A will have this form, the n by n matrices over D, and then center of A is a field, and dimension of A over center is bounded. Finally, Koplansky will to give a positive solution to the Courage problem for PI algebras. In other words, any algebraic PI algebra is locally finite. Now, remember that we had constructed this polynomial identity 5 for M2 of C. So Koplansky asked several important questions, including whether this phenomenon that we saw for M2 of C can happen for matrices of larger degree. For example, in Mn of F, can we say that there is a central polynomial, a polynomial that commutes with every element of the matrix algebra? So this led Formanek and Rasmussen to answer this question in characteristic 0 in 1972 and 73. And then from here on, there is this idea of T-ideals, which brings us to the some more recent work, especially in the past couple of years, and then the Speck problem for T-ideals. So first of all, if A is an algebra, we consider an ideal of the free associative algebra consisting of all identities satisfied by A. So for any algebra A, we are associating an ideal of the free associative algebra. We call it the T-ideal. So that T-ideal consists of all polynomial identities satisfied by A. So a couple of easy facts. T-ideals are closed under operations of substituting. And so then we say that the PI is derived from another PI. If when we substitute into variables of PI, we get the vanishing. And so then we can, on the other hand, we can associate a variety to every set of polynomials. So in other words, if we take a subset of the free associative algebra, we can associate all algebras. We can say variety. We can associate a variety to S, consisting of all algebras that satisfy all elements of S. So this is called the variety of S. This sort of resembles this notion of varieties from algebraic geometry, that the points in algebraic geometry corresponds to algebras in what you're talking here, polynomial identities. So in particular, if you take So what you see here, you take the T-ideal of A. So this consists of all polynomial identities satisfied by A. And then you take V of T of A. That turns out to be V of A itself. So V of A is closed under quotient, subalgebras, and direct products. Birkhoff says that the class of algebras is a variety if it's closed under operations of quotient, subalgebras, and direct products. And then if you take the free associative algebra mod out by the T-ideal of A, this will be what we call the relatively free algebra in the variety defined by A. So this was the same sort of constructions that people did when they were trying to solve the Burnside problem, restricted Burnside. So you're trying to take the biggest object in this variety. So we call it relatively free. So it is the object that is free, and every element in that variety will be a quotient of that object. A quotient A, in particular, A itself will be a quotient of this relatively free algebra. Now, suppose that we have, so a couple of examples. Suppose that we have an algebra that satisfies this identity. So identity of degree 2. Then in particular, we can see that, okay, so that's easy to see that xy is equal to yx. So A is commutative. And so you can map f of x1 to xn into A. And every polynomial identity of the polynomial algebra in two variables is a consequence of this identity. So this may sound trivial because it's commutative, but so in other words, fx is the relatively free algebra in the class of all commutative algebras. Every free algebra will be a quotient of f of x. So this may sound trivial, but if you go to Grassmann algebra, you see that things can quickly become untrivial. So first of all, in the Grassmann algebra is a vector space which is spanned by E1, E2, and so on. And then you will have these relations that EI squared is equal to 0. So you have this anti-commutativity relation between them. So monomials of this form, if you sort them out so that the index will form a basis of G, and G satisfies is nilpotent of class 2, satisfies this identity. Now, the interesting thing is that every other identity of G is a consequence of this Lie identity in characteristic 0. This was the part that was proved by Latyshev, and then later on extended to other positive characteristic by Regev in 73, a couple of years later. So this is the part that it becomes non-trivial if you go. So in the previous example, we had the commutative algebras, which was nilpotent of class 1. And then if you go to nilpotent class 2, which is the Grassmann algebras, things become completely untrivial, because here you have to show that every identity is a consequence of this Grassmann identity, which is not trivial. So then Specht in 1950 asked, if you have an associative algebra, you can form the T-ideal of that algebra. And he asked whether this T of A is finitely based. In other words, if you think about, like, it's not like Grobner basis, but it is sort of, you're looking at an ideal within the free associative algebra, and you're asking whether this ideal is finitely, we say it's finitely based because the way we generate T-ideals is a little bit more than ideals in the algebras, because here you also use substitution. So that's why Specht is asking whether T of A is finitely based. In other words, does there exist a finitely many identities in T of A, so that every other identity is a consequence of these identities? Okay, so can we get and prove that every T-ideal find a set of elements so that generate the T-ideal in the sense of T-ideals? Well, then Kurosh and Lobov showed in 1973 that yes, if A is finite dimensional. And what about the identities of n by n matrix? So this is one of the first example that comes into my mind, people's mind when they try to answer in positive or negative. So so this is only more or less known for n equal to 2. For example, M2 of F satisfies the S4 as well as this identity that we saw of degree 5. And Rasmussen showed that M2 of F, the identities of 2 by 2 matrix over F, consists of 9 polynomials of degree less than 6. A lot of people made contribution, especially Terensky made a lot of contribution to the T-ideals of matrices, upper triangular or MN, but it is still not fully known what's happening beyond 2. Amitsu and Procesi showed that Fx over T of Mn, T-ideal of n by m is a domain, and then Rasmussen, McKemmer, and Brown showed that the Jacobson radical in a affine PI algebra is nilpotent. So this is a fundamental theorem that will be used throughout. And furthermore, for example, another important applications of polynomial identities that polynomial identities distinguish Mn and its proper subalgebras. So now I'm going to move towards this more recent stuff about T-ideals. A polynomial is called linear if occurs at so degree of each generator is 1. So that these are called multilinear polynomial identities. If characteristic of the field is 0, then all T-ideals of the free associative algebra are generated by multilinear polynomial. This process is called multilinearization. You can essentially introduce more generators and essentially linearize each degree. Then part of literature is that A and A tensor K satisfy the same polynomial identities for every extension of the field, as long as characteristic is 0. And then if C is a infinite integral domain and G is an element of the polynomial ring over the C, then G will be 0. Okay, as long as G, if you substitute every arbitrary elements in G and you get 0, the only possibility for G is that G itself is 0. So this again resembles this idea in algebraic geometry. Okay, so then we get to representable algebras. An algebra is called finitely is called representable if you can embed it into a matrix ring over some commutative ring C. Given a finitely generated PI algebra over an infinite field, so we ask whether every PI algebra is representable or not. Well, we see that A is representable if and only if A is PI equivalent to a finite dimensional algebra. So here is where the Kemen's result come into play. First of all, he proves that a finitely generated relatively free algebra is representable. And then, so in other words, it follows that finitely generated PI algebra is PI equivalent to a finite dimensional algebra. He actually proves something more, stronger than what we are stating above, that every PI algebra is PI equivalent to the Grassmann envelope of finite dimensional superalgebra. And then, so he deduces that the T-ideal of finite generated associative algebra where character is 0 is finitely based. So this is a positive solution to the Speck problem. But this raised a lot of controversy. So he published his result in this monograph, which is translated by MS. But it raised a lot of controversy, so I'll get to that. Because a lot of people were using this result, and then a lot of people were doubting this sort of result. First of all, one result that we know for sure, so we'll get to that Jacobson radical of affine PI algebra is nilpotent. So this is, for a while, it was known to the Brown theorem, and then once the literature was revealed, it turned out that Rasmussen and Kemmer also proved that in a separate publication. So this is a fundamental result now that that is being used over and over. But the Cambridge result extends beyond this, and you get to the point that Procesi in 2014 put this paper in the archive and essentially saying or asking for verification about the Cambridge result. And a couple of people came for rescue. Essentially, Al-Hadaf in 2016, even more recently, I think 2 years ago, they gave some preprints filling the gaps or essentially explaining in more details how things evolve and work out in Cambridge construction and validating his claims that yes, so Cambridge results essentially are true now, and it can be freely and hopefully without mistakes used. Now, now I'm going to go to smash products and mention some of the recent works that in the past couple of years I've done myself, and this part is joined with Salvatore. So among the categories that PI has touched upon and is interesting is categories of groups and group rings, and also categories of enveloping algebras. So I want to connect these two categories and see what sort of role polynomials play there. So first of all, a group acts on algebra if there is an automorphism from G to the automorphism of A. Then by linearity, because FG is a half algebra, as a half algebra acts on A by making A and FG module. So you can construct this, we call it a smash product of A by FG. To make A smash FG into an algebra. So that is the multiplication. So in particular, of interest would be the case that G acts on a restricted Lie algebra by restricted Lie algebra automorphism. So then you can form the smash product of little u of L, where little u is the restricted enveloping algebra of L, by the group ring FG. And we're going to ask ourselves when this algebra satisfies a polynomial identity. Well, first of all, Bahturin and Petrogradsky showed when this smash product satisfies a polynomial identity. But we want to see if we were to restrict ourselves to specific polynomial identities. For example, we want to see when this smash product is nilpotent or when this smash product is solvable. So what are the conditions on L and G and also on the action of G on L? So clearly, this smash product contains both U of L and FG as subalgebras, copies of each. So if this wants to satisfy the polynomial identity or a specific polynomial identity, say, for example, nilpotent, then UL and FG itself must satisfy that polynomial identity. So this brings us to the result of Passman, Passy, and Segal, that they classified when FG is nilpotent. So that depends on the characteristic of the field. So they give the conditions on G so that FG is nilpotent. Similar questions for restricted Lie algebras were answered by Riley and Shalev, characterizing when U of L is nilpotent in terms of the conditions on L. So we want to put these together and then see when the smash product of UL and FG satisfy is nilpotent. First of all, we need this definition. We say that a group G acts nilpotently on a vector space V if there is this chain of subspaces of V which are G stable and the action of G on each quotient is trivial. So this would be the same thing as saying that the augmentation ideal of G to some exponent acts trivially on V. Now, so we show that suppose UL smash FG is nilpotent. This happens if and only if. So you have those restrictions or conditions from Passy and Segal and Passman, as well as the conditions that you bring with from Riley and Shalev. And then, so because it's the action, G is acting on L, so we would need to know what sort of specific action we get from action of G on L. So this would be the extra conditions that we need for U of L smash FG to be linear potent. So the proof breaks down in a couple of pieces. So first of all, we need this lemma. So this is part of the fundamental part of the proof. Then the whole actual proof, it breaks down into proving by induction on the nilpotence class of G and also nilpotence class of L. And we will also use simultaneous triangulation. And then we also focus on another specific class of polynomial identities being least solvability. We say we want to see when the smash product of U of L and FG is least solvable. So first we see when the group algebra is least solvable. This was again Passy, Passman, and Segal's result. And then similar result was done by Riley and Schaller for restricted enveloping algebras. Now we put these together and we say the smash product of U of L and FG satisfy least solvability if and only if these conditions are satisfied. So you have the first part coming from Passman and Segal and Passy. Second part is coming, so this part is coming from Riley and Schaller. And then we also have the action that is what we actually put everything together, and that's how things work out. So if you were to work on ordinary algebra, so all what we talk about is for restricted algebras. Ordinary algebras, you can quickly deduce the conditions for the smash product of UL and FG to be least solvable, because UL can be recovered as a restricting enveloping algebra of the P envelope of L in characteristic P or positive or 0. We have to exclude characteristic 2. Then, so essentially UL smash FG, if it is linear potent, then the structure, there is not much in terms of the structure. First of all, L is abelian, G will be nilpotent, and then the action will be essentially the trivial action of G on L. So there won't be much when you're asking UL smash FG to be linear potent. Like I said, we have to exclude the case that P is equal to 2 because there is counterexamples, and so P equal to 2 is a special case. And then we can apply this to co-commutative half algebras in characteristic 0 and say that H is least solvable if H is co-commutative over characteristic 0. H is least solvable if and only if H is commutative. Well, so there's this famous construction of Cartier constant Milnor that shows that in characteristic 0, every co-commutative half algebra is of this form, is of the smash product of U of L and FG. Well, you can specify what the L is and what his G is in terms of the primitive elements and group-like elements. Now, there is this Sudler half algebra, which is least solvable, but it is not commutative. So we are asking whether we can drop this co-commutative conditions that we had up here. We cannot drop it because there is this example of Sudler, which is least solvable but not commutative, and the reason is, and the reason that we cannot deduce that it's not commutative because H to begin with is not co-commutative. So I guess I'll stop here. That's all I wanted to present. Thank you.
Okay. Thank you, Hamid, for this interesting talk. Are there any questions, comments, or remarks?
So I'm going to stop my share.
I don't see any questions. So in this case, let's thank Hamid again.
Thank you.
And